Hello, everyone. Yeah, yeah. So I will begin by first thanking the organizers for putting up this very nice workshop, and special thanks to Arnab and Rodrish, who are also part of this collaboration. The details of this thing you will find in this PRB, and so in this talk, what I will try to explain that there are certain beyond Kibble-Zurek signatures when you measure certain observables, and I will tell you what that is. And for this particular talk, I will focus completely an integrable spin chain. And I hope to clarify things, what I exactly mean by beyond Kibble-Zurek and what not. Okay, so and the final result is very brief, yet very intriguing. So I might just finish before the stipulated time. Okay, so I know that an introduction to Kibble-Zurek is not quite necessary for this audience. It's very well known to a big fraction of this audience. Some of you have already worked extensively on this thing. But still, in view of connecting everyone, I would like to start with simple settings. This is known to us that when when a system houses various phases, there are phase transitions between them, and particularly when you drive certain parameter that can take you from one phase to another phase. That parameter can, for example, be temperature when there are classical phases and phase transitions, or in quantum phase transition that can be some coupling. So what happens in the standard theory of Landau description that an ordered phase is sort of described by some finite value of the ordered parameter, and when we talk about continuous phase transition, this value of this finite value of this ordered parameter decreases continuously and to zero in the orderless phase. Okay. And associated with these phase transitions, there are certain length scale and time scales in the system, and particularly close to these phase transitions, fluctuations diverges. So we also know that for a simple system near this criticality, this lambda c, the correlation length diverges, and also the relaxation time of the system diverges, and you can there is a simple power law description between the time scale and the length scale in the problem, and the z is called the dynamical critical exponent. Okay, so now if we ask the questions of how order set in when we drive across the phase transitions. So one picture which was envisaged by Tom Kibble around 1975 said that generally in the system which is being driven through a phase transitions, order sets in by creating domains in the system. Okay, so that these are the domains in the system, and in each domain the order parameter can be thought of as approximately uniform, but then it can change between various domains nearby. For example, if you think of a complex order parameter, the phase of that order parameter can be different in different nearby domains and the domains which are also far apart. And then it is expected naturally those domains, when they come together in this setting, they can trap something which is known as defects. Okay? So here in this picture I have shown point defects in the system, but these defects can be line defects and other types of defects of various codimensions. And it turns out that when the system eventually coarsens at infinitely large time, these defects, which are some kind of like a proto defects or seeds for defects, then some of them survive, and those who survive, these are known as the topological defects in the system, and these defects are then very far apart from each other, and there are these microscopic separations in the system. So what happens is that it starts with some seeds of these topological defects, and then many of them will die over this process of coarsening, and then those which will survive, their number will also be the proportional to the number of these seeds in the system. And you can simply compute the density of these topological defects using this formula, where this I equilibrium is this separation between the defects at long times. Right? And the type of defects that will generically appear in the system, as I told you, these point defects versus line defects. So that involves the homotopy groups of the symmetries that is there in the orderless space and in the ordered phase, particularly the coset space of the various symmetry groups in this problem. And and then various homotopy groups, various non-vanishing homotopy groups will give you the type of defects you can have in this system. Okay. Okay. So then roughly 10 years after Keibel Spey, Zurek put it on a very strong footing when he was thinking of having a very similar picture of quantum phase transitions, or phase transitions, not quantum phase transitions, just so phase transitions in condensed matter setups. Okay, and here is the picture which is now known as the Keibel-Zurek mechanism. And let me explain this picture in bits. So it relies on it relies on 3 stages of evolution close to a critical point when a system is being driven through through this critical point. So far away from the critical point, okay, we can expect the system to behave it's following the protocol. So it's an adiabatic evolution here. Suppose I'm using a driving protocol which is linearized around this critical point. Okay, so you can have other type of nonlinear protocols as well, and but if you linearize that thing here, and this is the driving parameter, and with this linearized drive, I have a time scale which is given by this tau q. Okay, so that's the ramp rate in this for this particular protocol. And we know that these intrinsic, these time scale, the relaxation time of the system, that also behaves in this particular way. So what you expect is that as you are approaching the phase transition, at some point this relaxation time will become much larger than the time associated with the change of these driving parameter. So when they equate, you get something called a freeze out time. And the meaning of the freeze out time is the following: then after this time, the system will fail to relax, and in this adiabatic impulse adiabatic approximation, what is taken is that the state of the system is frozen, and then after you have crossed the critical point, again when the relaxation time will be smaller than this particular time of this ramp rate, then the system will again start another adiabatic evolution in the system, another adiabatic evolution. Okay, so this freeze out time you can compute by equating the 2 time scale, which I will come to it shortly. But basically you see that under this full evolution in this adiabatic impulse adiabatic this approximation, you generate topological defects in the system, as I flashed in the couple of slides earlier, and you can compute these correlation length and the topological defects by this formula. And you can see that depending on these various tau q, there is a sort of an universal scaling appear, and the number of topological defects will depend on this tau q. So for example, if you drive very slowly, then there will be less number of defects in the system, whereas if you drive very fast, there will be more number of defects in the system. Okay. So that's known as this adiabatic impulse adiabatic picture. Okay, so this particular prediction of this Keibel-Zurek prediction, particularly involving these this defect density, the scaling of this defect density was then verified in several experiments. Of course, this list is in no way an exhausted list. So there are various experiments, and there are very decent experiments also, including the one which was flashed in Reinstock on programmable simulators. So it was verified in these experiments that this Keibel-Zurek prediction holds. Particularly the scaling law was verified in these experiments. Okay. Yeah. So it turns out that even though this is a very simple picture, adiabatic impulse and adiabatic picture, and in the impulse region, we have basically considered that the system remains frozen. So still, it turns out that there are substantial dynamics takes place in this critical region, particularly, and there can be situations or there can be observables for which this simple adiabatic impulse adiabatic picture may not predict the behavior. Okay, but nonetheless, as I told you that it was there are it was shown that these the prefactors of these scaling of these defects that can change, but basically this scaling law still holds. And in recent, not very recently, but in some of the work, it was also predicted that there can be some corrections to these Ebel-Zurek scaling. Particularly in this paper, the author suggested that this particular scaling law will be modified when you consider this kind of near adiabatic annealing. And even though this was a classical setting, but it turns out that this is a very robust feature of Keeble-Zurek mechanism, and even if you compute the full defect density distribution, and if you compute the various cumulants of the density distribution, you can still see variance of like this kind of scaling emerge in those cumulants. Okay. Yeah, so so having said that, in this talk, the focus is that we would particularly like to go beyond these density calculations of defects, and rather look at something which is the correlations among the defects. So we will explicitly compute correlation functions among the defects, particularly the topological defects in the system. And for that, we will consider a very simple quantum setting. It's an integrable spin chain, which we will drive linearly. And I will come to the details of the model. And we will see that if you compute the defect-defect correlations, even in this simple quantum setting, you still get features that cannot be explained in a adiabatic impulse adiabatic picture. Okay. So with that, let me now introduce the system. It's a very simple system which is extensively studied. So it's a transverse field Ising model, and this transverse field is now a function of time, and it's driven across a phase transition. So there is a phase transition here in this model at g equal to 1 and g equal to -1. There is a ferromagnetic phase in between, and then there is a paramagnetic phase when g is very large. Okay. So what we will be doing here, we will focus on this part of the phase diagram. So we will drive this system from a very large G to somewhere in the middle of this ferromagnetic phase. So we will stop exactly at G equal to 0, so that we are deep into the ferromagnetic phase. And then we will compute what happens to the correlation functions. Okay. But having said that, I would still like to mention is that our results still hold if you ramp it all the way to the other end. So and all the features that I will be flashing, they also appear if you cross the critical point 2 times by completing this phase diagram. So yeah, so that's the protocol, and what I will be computing is the following. So here is a snapshot of the configurations where you can see these are identified as the defects in the system, and the formula the formula of the defects, the formula for the defect density is the following. That is a product of these two operators, because we want to compute the defects in the ferromagnetic phase. So and then when the product is negative, the -1, then you count a defect. Okay, and then again, if you compute the defects, there are several authors. Some of them are present in the audience, and they have computed these things, and indeed, it's an exact calculation. So you can also compute the prefactors exactly here. But the upshot is that you recovered this the Keeble-Zurek scaling here. Okay, so for this particular system, this dimension is 1, this nu is the way the correlation length grows, this exponent is also 1, and the dynamical critical exponent is also 1. So the defect density basically behaves as tau q to the minus half. So that's the one which is computed here. So we focus on these defect correlation function. And so the defect correlation functions, as I told you, the way I defined the defect operator for me, then the correlation functions behave like this. Okay, so it's a connected correlation function between the defects. So there are two defects which are separated by a distance r. So there is one defect at, between the sides j and j plus 1. There is another defect between the sides j plus r and j plus r plus 1. So one standard way to compute these defects is that you change the spin variables. It's a very standard technique in computing various parameters in the transverse field Ising model and in many other systems. In 1D particularly, what you can do, you can transform this spin variable to hardcore bosons, and then you can go to the non-local fermions by Jordan-Wigner transformation. But it turns out that if you do all these things and apply here, this will give you a pretty complicated structure in terms of these fermions. There will be complicated determinants involved in this full thing. So we rather take a simpler route in this problem to compute these defect correlations. Okay, so and the route is the following. So what you do, you introduce the dual variables. Okay, so these are one known example of what is known as the Kramers-Vanier duality. So so if you introduce these dual variables involving this original spin variable, and then your Hamiltonian now transforms to a very similar looking Hamiltonian, which is expected in this case. There is a self-duality point also because this model is self-dual. And then if you use now these dual variables, it turns out in terms of these dual variables, these the defect correlations becomes particularly simple. It just becomes the density correlations. Okay, and you can completely compute the wave functions in this dual prescription. You can do solve the time dependent Schrodinger equation, and what you get is the following now. So again, if you focus on this very slow ramp limit where my tau q is very large compared to the energy scale j in the problem, it turns out that these defect correlations, after these kind of approximations, that the solution which you get from this time dependent Schrodinger equation. So these are complicated periodic cylindrical functions, and then you take the limiting cases for this particular limit, and then you also approximate that you want to look at the long wavelength excitations in the problem for which the excitations is the highest. So with these approximations, if you compute the defect correlations, it turns out that you have a very clean Gaussian decay in the system. Okay, so we have verified this in numerics. So if you do some simulations over a chain, here I think the number of sites in the chain was taken 10 to the 4, and it turns out that for these large values of this tau q, we have a very clean demonstration of the Gaussian decay in this system. Okay. So having said that, we now ask that this Gaussian decay is very unusual. We do not often encounter quantum systems where some correlation function is behaving in a Gaussian way. Okay, most of the time what we encountered is either some algebraic function or typical exponential decay in the system, depending on the spectrum of the system. So in this case, so this was a startling result for us when we got this Gaussian decay. And and we also, particularly if you compute the spin-spin correlation in the system in these sigma x direction, then this does not cleanly show an expected exponential behavior. Okay, so it's these particularly these defect correlations which gives you the Gaussian decay, and you can also compute these defect correlations in the transverse directions, and that also gives another Gaussian decay. Okay, so one thing to note here, first of all, is that you can see the correlation length associated with this Gaussian decay. That is according to the expected Kibble-Zurek scaling. You remember that I told you that n, the defect density goes as tau q to the minus half. So the correlation length, which will be inverse of the defect density, that will go as tau q to the half. And here you can see that that is still there. So we have a correlation length which is obeying the Kibble-Zurek scaling. But the behavior, as I will show you in the next part of the talk, is not explained by the standard adiabatic impulse adiabatic picture of the Kibble-Zurek mechanism. Okay, so as we investigated, so in the adiabatic impulse adiabatic approximation relies on the fact that the state is following adiabatically up to certain point as you are nearing the critical point, and then the state gets frozen, okay, and then after a certain time when you have crossed the critical point, you can again evolve the state adiabatically, okay. So you can see that the eigenstate behavior is very crucial, to basically explain what you get out of Kibble-Zurek prediction, okay. But if you now compute the defect correlations using the eigenstates of the system, you still see exponential behavior in the system. So the ground state, for example, okay, if you study the ground state, then you get very clean exponential. Even if you study the higher excited states of the system. So here, for example, we created certain excited state by selectively exciting certain K modes in the system. So this way you can get access to some of the excited states in the system. So even if you create states in this way and then compute the defect correlations in those states, you still see you still see very clean exponential decay in the system. So for example, here I have shown you one way to excite some of the modes selectively and create the excited states. So depending on these energy excitations, you can we have computed these correlations as a function of R, and you still see a very clean exponential behavior. Or sometimes it could also show some kind of, depending on the density of where you are in the excited spectrum, it can also give you some kind of algebraic behavior in the system, but certainly no Gaussian decay. Gaussian behavior was expected from these eigenstate calculations. So which made us make this conclusion that the adiabatic impulse adiabatic picture, as I flashed, is not sufficient to capture the complicated chaotic quantum dynamics associated with this ramp in the system. Okay. So now then we asked that, okay, are we getting something transient? Like if you stop right after the ramp and compute the defect correlations, you get very clean Gaussian decay, Gaussian behavior. And what happens if you now let the system dephase? So if you now stop the ramp deep into the ferromagnetic phase and just wait for some time and see what happens to this kind of Gaussian behavior. Okay, so it turns out, what you expect that starting from some state which you get right after you stop the ramp at g equal to 0, and then you allow dephasing in the system, you are expected to go to this diagonal ensemble. Okay, so basically the Gaussian behavior was so the defect correlation was Gaussian here. And it turns out, even if you wait for a long time, this Gaussian very neatly survives in the system, okay? And so we expect to have, so what we then tried to understand that what happens to if you compute the exact ensemble in this, for this problem, and it turns out because it's an integrable system, we know that there will be exponentially large number of the conserved quantities in the system. These are given by these density of these Bogoliubov fermions. And these are the Lagrange multipliers, which basically encodes the initial behavior of this evolution. So basically, it's a behavior right when the evolution started. Okay, so then it turns out after if you wait for a long time for these large tau q, we still see very clean Gaussian decay. So the Gaussian decay basically survives under dephasing. So what it implies is that there is a novel ensemble emerges, which we call as a ramp ensemble, and this ramp ensemble is the following. Under the dephasing, you get to this the generalized Gaussian ensembles with these coefficients. And if you compute these defect correlations here, so here rho is not the density matrix, but rather the the operator, which is the defect correlation operator. So if you compute that, it turns out that there is again no Gaussian information in this part of this expression because it involves eigenstates, and as I showed to you that no eigenstate can give rise to any Gaussian behavior in the system. But then the Gaussian has to come from these coefficients, which involve these Lagrange multipliers. Okay, so then what we found is that this Gaussianity in these long-term behavior of the defect correlations, it inherits through the history of this ramp, and we also find that there is no if you do any sorts of instantaneous quench in the system, you will not see any such Gaussian behavior. Okay, so it's very specific to this ramp in the problem. So that's why we term it as a new ramp ensemble. Okay, that includes this Gaussian behavior. Okay. Okay. So we also I would like to flash this thing. This is particularly interesting is that we also then ask this question that how these Gaussianity in the defect correlation sets in. See, when you are very far from the phase transitions, you don't expect any Gaussian behavior, okay? Because these are sort of adiabatic evolution of eigenstates, so you expect clean exponential decay in the system. But then it turns out that there is a particular scale, particular time scale over which this Gaussian behavior sets in as you approach the critical point and you cross the critical point. Okay, so what I have plotted here, so you can, so for our data, what we obtained from the numerical simulations, you can compute this correlation coefficient, which is known as the Pearson correlation coefficient for this particular data. So if it is a clean Gaussian decay and you fit this data in this way, then this coefficient being 1 will say there is a perfect Gaussian correlation. Okay. So now if I plot this quantity as a function of these ramp parameter g, we see that far away from the critical point you expect deviations, pronounced deviations from 1, at which you can see here, but then as you gradually approach the critical point, this should approach a value which is 1. Okay, and it turns out that if you scale this parameter with an appropriate scaling factor given by the time, the time associated with this ramp, which is tau q to the half, because you remember that the xi goes as tau q to the half, and the dynamical critical exponent is 1. So you also know that the time scale will also go as tau q to the half. So you see that there is a very nice scaling collapse here. So basically, this Gaussianity sets in over a time scale in this system, which again obeys the Kibble-Zurek scaling. Okay, so these are the two things which mark some reconciliation with the Kibble-Zurek picture for this particular observable, that the length scale xi is tau q to the half, and the time scale over which the Gaussianity sets in is also tau q to the half. Okay, and you can see that it's a very clean plot here that reveals this tau q to the minus half feature. There are some explanation which we still do not have quite clearly that how these oscillations are coming in, but again we can at least concretely understand something about the time scale over which we are getting this Gaussian behavior in the system. Okay, so now some final remarks regarding whether you can expect to see this kind of Gaussian behavior in some experimentally accessible regime. So one system was already flashed in Ryan's talk, these programmable Rydberg simulators, and there are superconducting qubits also, for which they can at least simulate for simulator ramp for which this tau q is of the order of 10. Okay, I think they can go beyond it if in the superconducting qubits. But in this regime of tau q, and particularly if we simulate it over a small number of sites, which is again experimentally doable there, we see that we still have remnants of Gaussian decay here. It's very clear. It's slightly enhanced because now you have in this values of tau q, we have many number of defects in the system. But if you compute the correlations again between these defects, you do see that and they are Gaussian correlated in the system. Okay, I think yeah, I think that brings me to the summary of my talk. So what I showed in the talk is that if you run a critical ramp in an integrable spin chain, you see that it can produce a Gaussian spatial decay. When you compute, when you go beyond computing a density of defects and look into the correlations between the defects, okay? And even though if you compute the spin-spin correlations in the system, you still see exponential decay, but the defects behave in a very distinct way. And one particular way of understanding this kind of Gaussian behavior is that the defects are sort of behaving like bosons, free non-interacting bosons above the degeneracy temperature, and free bosons above the degeneracy temperature, their density correlations can show this kind of Gaussian decay. And of course, if you now decrease the temperature, they go below the degeneracy temperature, and if you include interactions between these bosons, still Gaussian tail appears, but this kind of interactions modifies the short distance behavior in these defects. So to a reasonable approximations, we believe that these defects are behaving like free bosons in an effective thermal soup, for which their correlations is Gaussian. And we also found that we cannot explain this Gaussian behavior using the adiabatic impulse adiabatic picture, which is the crux of the Kibble-Zurek mechanism. And it turns out that these ramp and other continuous drive protocols, it also applies to other nonlinear ramps as well, that they indeed generate the stable non-equilibrium ensemble, which we termed as this ramp ensemble, which is pretty exotic, and it has properties that are not inherited from the eigenstates. And so that features that the actual dynamics which is happening in the impulse regions is pretty chaotic, and one needs to go beyond this impulse approximation. Yeah, so finally an open question in this regard would be that how this quantum coarsening takes place in these 1D systems that can possibly give us some indications that why you may expect departure from the Kibble-Zurek picture in this problem. That remains an interesting question. Yeah, I think with that I would like to.
Thank you.
Not the correlations function, I guess. Yeah, the correlation functions are not computed, even for the classical case. So you can, yeah, so these defect, the scaling of the density of defects are computed for certain classical transitions. And as I said, that there are, corrections to Kibble-Zurek prediction. But I think the correlations among the defects are not calculated.
But do you think the same Gaussian decay will hold there also?
It may not be. They can just simply show an exponential decay for the thermal fins or here, I guess.
Yes.
Yeah, just one question. Do you expect it to hold in a similar manner in higher dimensional integrable models like the Kitaev?
Yeah, that I believe so. Yeah, I think, yeah. I think
you'll also see a Gaussian?
Yeah, I expect to see a Gaussian in these integrables.
The reason I'm asking is that there is a critical surface and not a point, and whether that changes.
Yeah, I think that we have not explicitly computed that, but I don't think that's a crucial thing for this particular case, because we know how that changes the Kibble-Zurek scaling, right? The codimension of the defects, we know that how changes the scaling with the tau q.
Sure.
Yeah,
that we know.
Yeah, but I think
just asking that whether that changes.
Yeah, I think as long as for the integrable systems, I believe these behaviors will survive. Yeah.
So this is a comment to this question. So we wondered in what kind of systems we can see probably this kind of Gaussian correlations. to our surprise, we found this happens to occur in bosons in the non-degenerate limit when they are very rare in densities, 1 or 2-dimensional bosonic system, bosonic gas basically. And that means we can interpret our defects as basically bosons, and the background, though it's an integrable system, is chaotic enough when you do these things. So the defects become like isolated a gas of bosons. And then this Gaussian correlation can be physically understood, physically maps to that. We are not sure exactly that is happening because it's an integrable system, so a thermal superboson is not guaranteed. But it seems that can be of something close to what you say. So I believe if you can create defects which are in a classical system, I don't know whether that would be possible because of the interactions between the defect will be very different in a classical system. So if you somehow can eliminate these interactions and make a gas of bosons, I mean, it's not necessarily bosons because degenerates are almost classical, then there is a possibility you'll see this Gaussian decay even in classical system.
I was just thinking that if you just take the standard classical phase transitions that we know have the Kibble-Zurich, if you just go and compute, do you actually?
Yeah, I mean, that's what I'm saying. There is no guarantee. So the underlying physical picture we have is a gas of defects, which are like behaving like degenerate boson gas.
Classically, what does that mean? Bosons, I don't.
That means these defects are local, and actually the spin-spin correlations are non-local, as you know. I mean, but the defects are local, and they are very far from each other to have any interaction.
Yeah, so like a free particles in that sense, obeying Maxwell-Boltzmann in that. Right. Then you can see that because of this e to the minus x square will be there, so you might expect some Gaussian decay, the density correlation. If that situation can be obtained,
I see.
In the classical setup, yeah.
Okay, any further question? Yes?
So Krishan, since you're saying this is special to integrable models, presumably integrable models don't go to a thermal, but some sort of a GGE,
Yeah.
likely. If you started assuming that it went to a GGE, would there be a way of getting Gaussian rather than the exponential out
No,
of
that's
that?
what I showed you. This ensemble, this ramp ensemble that emerges,
Yeah.
that remembers the history of the ramp.
Yeah.
And that actually gives rise to the Gaussian and these Gaussian correlations for the defects.
No, that I understand. I'm just saying that if I just assumed a GGE without figuring out all the dynamics, I know the overall constraints, I just write down a GGE it goes to, would it have essentially given you the same answer rather than saying it goes to a thermal distribution?
Well, the constraints are time dependent here. So in general, I would expect, sorry, I'm answering this question. So in general, if you just say that we start with this state and we have this final Hamiltonian, which is our t going to infinity Hamiltonian, you're not going to get this. You're going to get exponential decay. So you need the history of this ramp to create this complexity somehow.
Okay, thank you.
Yeah, and for instantaneous quenches, you will never get it actually. So you will just get some exponential for the correlation.
Okay, so let us thank Kishore again.